Okay, this is the solutions here for the review for your exponential and logarithmic test. All right, the first one here, they give you a logarithm equation and they ask us to put it in exponential form. So what we're going to use here is the same basic definition of what a logarithm is. Okay, and so that says if I take my base and raise it to this power, that it should be equal to that number. So b to the y equals x. And notice we're not really solving for x, we're just switching the form. So this would say here that 4 to the third power is equal to x. And now that's in an exponential form. Okay, on 2, 3, and 4, we're asked to evaluate. So we're going to use that same basic principle of a logarithm. And so on number 2, what we're going to look at is we're going to ask ourselves this 5 here, this base. 5 raised to what power would be 125. So notice 5 squared would be 25, but 5 cubed would be 125. So this answer there would be 3. And now for number 3, now this one has a fraction. And so what I'm going to focus on here is just the 8 part. So 2 to the third would be 8. Now, because that's 1 over 8, I just need to make that negative 3. Because here I'm going to use this property here. If we say x to the negative 3 power, this means 1 over x cubed. Okay, on number 4, one thing we may want to do on number 4 is when we have a logarithm here and a radical, we can write this radical, it's the square root of 5. So instead of writing it as the square root of 5 here, we could write it as 5 to the 1/2 power. So we can ask ourselves the question here, 5 right there raised to what power would be 5 to the 1/2 power. So that would just be 1/2, because we'd have 5 to the 1/2 equals 5 to the 1/2. Now, you may not have, you probably didn't need to write that way, but you could there if you needed to. Okay, on 5, 6, and 7, I believe you're asked to graph here an exponential or a logarithmic function. So this one's exponential. Now, when we're graphing an exponential function here, what we're trying to find for two values here, we need two values of x that make the exponent 0 and make the exponent 1, and any kind of vertical shift will give me a horizontal asymptote. So let's find our values right here that would make that exponent 0 or 1. So what would make that exponent 0 there is if x was 1. So if x was 1, we would have 3 to the 0 power plus 2. Well, 3 to the 0 power is just 1. Anything to the 0 power is 1. And then 1 and 2 would give me 3. Okay, now let's figure out what makes the exponent 1 here would be the value of 2. 2 minus 1 would give me 1. So we would get 3 to the first power and then plus 2. 3 to the first power is 3, and then 3 and 2 would be 5. And so now I've got me two nice points here to graph a curve through. Now all I need to know is what is that curve chasing? So an exponential is going to have a horizontal asymptote. And so that horizontal asymptote is going to come from that vertical shift right there. So it's going to be y equals 2. Now let's graph this. So we'll start with my horizontal asymptote at y equals 2. And then we got the point 1, 3, and then 2, 5. Okay, so now we have to do is draw my curve through these 2 points here, and it's going to chase this asymptote. Okay, now, wrong way. All right, on number 6, now we've changed here to a logarithmic equation or logarithmic function. So the idea with the logarithmic one here, first off, let's write it as y equals. But the idea is to switch this in exponential form and sort of take the same approach. So exponential form here would be 3 to the y power equals x minus 4. And now I'm going to solve for x here. And so to kind of recall the steps, what I want to do here is to put it in exponential form is isolate the logarithm, which it's already isolated. And now that I've switched it to exponential form, I'm going to solve for the x. And so I'm going to get 3 to the y minus 4 equals x. Now we're going to treat it just like we did earlier with the exponential. The only difference here is it's not y equals, but it's x equals. So what we're going to do is choose values of y that makes the exponent 0 and 1 instead of using values of x. And instead of a horizontal asymptote from the shift, we're going to get this shift here of minus 4. That's going to be a vertical asymptote. So things kind of just turn around, flip around a little backwards here. Now, let's put in values that make the exponent 0, which would be if y was 0. So we would get 3 to the 0 minus 4. So 3 to the 0 power, or anything to the 0 power, is 1. And so 1 minus 4 would be negative 3. Now, let's see what would make the exponent 1 is if y was 1. So we get 3 to the first power minus 4. That would just be 3 minus 4, which is negative 1. Now, so the shift in the function here, the minus 4, instead of being a horizontal asymptote like it was when I had an exponential one here, when I've got a logarithmic one, that shift is going to be a vertical asymptote. So we'll have a vertical asymptote of x equals negative 4. Now let's graph this. We'll graph the asymptote first. So x equals negative 4. That's my vertical line here that's going to be chasing. And now I've got two nice points, negative 3, 0, and then negative 1, 1. And all I do is draw my curve and then chase that asymptote there. Okay, now number 7 was real similar. Kind of notice the differences here. In this case, the x minus 4 is the logarithm. In this one, though, the only logarithm there is x. So before I switch this into exponential form, right, that is y equals, I have to isolate this one first because the minus 4 part there is not a part of the logarithm. So I'm just going to add it over first. Okay, now I'm going to go to exponential form. So it's going to say 3 to the y plus 4 power equals x. Okay, so now let's pick our values of y that make the exponent 0 and 1. So what would make our exponent here 0 is if y was negative 4. So we would just get 3 to the 0 power, which would just be 1. Now what would make our exponent 1 there would be a negative 3. So negative 3 plus 4 would be 1, and 3 to the first power would just be 3. Now notice this one doesn't have any kind of a vertical shift to it here, or horizontal shift actually. I'm not adding or subtracting anything. The plus 4 is in the exponent. So the vertical asymptote here is just going to be x equals 0. So we graph that first. So that's basically what's along the y-axis there. So I'm going to be chasing the y-axis. Now I'm going through the points 1, negative 4, and then 3, negative 3. Okay, so now all I have to do is just chase that asymptote there and go through those 2 points. All right, on 8 and 9 here, we're asked to expand these, and what we're doing is using our properties. So recall here that number 8 is using the quotient property. So with that division, what I can do is expand this into 2 logarithms that subtract. Okay, now I can keep expanding here, especially with the second logarithm there. I can use my power property on the 3 and bring the 3 out in the front here. So we'll just erase it and put it in the front right there. Now recall or read the directions here. I don't have them all written out, but it said if anything, if I could evaluate a logarithm to sort of do so. So notice the first logarithm right here, log base 5 of 25 can be evaluated. because 5 to the second power is 25, and this will just be 2. Okay, number 9. Now, on 9, this one's kind of similar here. This one is multiplying instead of dividing. So with the multiplication, we're going to split this up into 2 logarithms that add. So this would be plus log base 2 of, and now instead of writing square root of x as x, I could write it as x to the 1/2. Okay, now there again, I'll use my power property. And so I'll bring the 1/2 out here to expand it. And now notice that the first one that I've got here, log base 2 of 8, can be evaluated because 2 to the 3rd power is 8. So that would just be 3. Okay, now number 10. One thing that we should look at on number 10, especially that denominator there of the 5th root of z. Let's rewrite that first. Okay, a lot of times with logarithms here, we don't want to think of terms of radicals. We want to think of it in terms of exponents. So the 5th root of z would be the same thing as z to the 1/5 power. Okay, now let's expand our logarithm here. So notice we've got multiplication here and then division here. And all these powers, the 2, the 3, and then the 1/5, are just going to come out to the front there. So now let's expand here. So we're going to get log base 6. Now, with the x squared, the 2 is going to come out in front with the power. And we got times y cubed, so we'll say plus 3 times log base 6 of y. And then the division here means we're going to subtract. So we have minus. Now we're going to bring the 1/5 power to the front. So it would be 1/5 log base 6 of z. Okay, notice all those were unknowns there, so I'm not going to be able to evaluate any of those. Okay, number 11 and 12 here, we're just doing the opposite. We're actually condensing. So we're going from maybe 2 or 3 logarithms down to just 1 logarithm. So with the addition right here, what I'm going to take 50 and 2 and do with those is actually multiply. 50 times 2 would be 100. So I would get the log of 100. Now, there again, if we can evaluate this, we need to, and we can evaluate this one. Well, we have to understand here that the understood base that's not written right there is 10. So we can ask ourselves 10 raised to what power would be 100, and so that would be 2. So this would just be equal to 2 there. Now number 12, in this case we've got some natural logs. Really doesn't matter that they're natural logs. We can expand them just like they were just normal logarithms or common logs. Now, notice in this one we've got the subtraction, so we're going to change this to division. But one thing that we need to do first here, if we're condensing, we've got to follow the order of operations. So we're going to use the power property first. So I'm going to move the 5 right here and then the 2 right here to my exponent. So this is going to be the natural log of x to the 5th minus the natural log of y squared. Okay, now let's use our quotient property. And so what we're actually going to do with x to the 5th now and y squared is divide them. So now it'll be a single logarithm. The natural log of x to the 5th divided by y squared. Okay, and number 13, we've got 3 logarithms. Now here again, what I'm going to do is use my power property first. So that'll give me log of x squared plus the log of y cubed minus the log of z to the 5th. And so now let's use our, in this case of the plus sign would be the product property, and then the minus sign would be the quotient property. So with product and quotient, that's multiplication and division. And when I do multiplication and division, I do left to right, or what comes first. So I'm going to do the multiplication first there. So this would be the log of x squared times y cubed. Now I'm going to do the division. So that would be divided by here, and then z to the 5th. Okay, now the rest of these are asking me to solve some equations here. Some of these are exponential and some of them are logarithmic. So notice the first three there are all exponential. Now the rest of them are logarithmic though. The main idea here is that I'm probably going to need logarithms to solve my exponential ones, and to solve my logarithmic ones, one of the main things here to do is use the definition of a logarithm and go to exponential form. Now on 14, you didn't have to use logarithms here. Now I'll kind of give you a little bit of assurance on the test. The directions will be a little bit clearer on the problem like 14. The idea is you can write both sides with a common base, and your directions are going to kind of give you a hint on that on your test here. But with 8 and 32, both of those numbers could be written with a base of 2. So 8 could be written as 2 to the third power. And so now I can write this as 2 to the third to the 2x. And then 32 could be written as 2 to the fifth power. So now we can use the idea is if the bases here are the same, then the exponents should be equal. So I'm going to use the power to the power rule, which means you multiply those. That will give me 6x. And then right here we'll multiply, basically distribute there. That will give me 5x minus 5. And now I've got an easy equation to solve here. And so we'll get x to be -5. Now it's okay for exponents to be negative. What we have to watch out with extraneous solutions is if I'm taking a logarithm of a negative number. Now, let's look at 15. Now, in 15, there's no way we're going to write 19 with a base of 4 or a base of 2. So 15 and on out here, 15 and 16, what we need is natural logs. So if I can't write with a common base, first thing we'll try to do is isolate that base, and that is already isolated there. So now the next thing, we'll take a logarithm on both sides, and we'll use a natural log. Now we'll take the natural log of both sides here. And so when I'm taking a logarithm or a natural log, I can use the power property to take my exponent here and move it out to the front and multiply. So we get x plus 1 times the natural log of 4 equals natural log of 19. And now I have it to a point here where I can solve for x. So I'm going to divide both sides here by the natural log of 4 because I'm trying to get x isolated right there. So we get x plus 1 equals, now let's see in the calculator here. What this is going to give me, so we need a natural log of 19 divided by the natural log of 4. Okay, so that's about here, it disappeared, 2.12. And now I'm going to subtract 1 from that. And when I subtract 1, I'm going to be sure that I don't just subtract 1 from what's on the paper. I subtract 1, not 4, from what's on my calculator there. About 1.12. Okay, for number 16, now the only difference here with 16 is that my base here of e is not isolated. And it does have a base of e, so there's going to be a shortcut with this one. But first off here, before we use a logarithm, we're going to have to get rid of the 3. Okay, so now I'm going to get e to the 2x plus 1 equals 10 over 3. Right, now I'm going to take a logarithm on both sides. I'm going to use a natural log on both sides. And now when I take the natural log of e raised to a power, we can just say the natural log of e to the 2x plus 1 would just be 2x plus 1. So using the power property is not necessary when you have a base of e and you use a natural log. Now, the natural log of 10 over 3, let's kind of calculate that. We'll punch in the natural log, and then I'm just going to basically push it in as division is 10 divided by 3. You could certainly use your fraction command if you wanted to, or you could take 10 over 3 and just use the decimal value. So that's about 1.20. Now, from there, I'm just going to solve it there. And so I would subtract 1, and then take whatever that is and divide it by 2. So I'm going to do it on the calculator there because I need to be accurate. So minus 1, and now that divided by 2. And so that's about 0.10 there. Okay, now for the rest of these, we're switching to log equations here. So with log equations, one of the main goals here that I want to try to do would be to switch it to an exponential form. Okay, so you kind of have two options here. We can switch it to an exponential form, like we're going to do in number 17, or if we have logs on both sides, and all we have is logs on both sides, we can just cancel them out. In this case, it's just one logarithm, and it's already isolated, so I'm going to go to the exponential form. So the exponential form is going to say this number raised to this power is equal to this value. So we'd have 3 to the negative 4th power equals x minus 1. Now, 3 to the 4th power here would really be 1 over 81, I think. But really and truly, all we need to do is just use the calculator for this. So my calculator, I'm going to punch in just 3 raised to, and now the negative 4th power. And so that's about 0.01. Now, I'm going to add 1 to both sides. And again, I'm going to add 1 to what's in my calculator. So it's like really accurate here. So it's about 1.01. And number 18. Now this one's a little different here. It's a natural log, but I'm still with one logarithm trying to get to the same premise, trying to get to exponential form. Now we need to isolate this one first because we've got that 4 in the front. So let's just divide off the 4 instead of using the power property. Give me the natural log of 2x equals 3. Now from this point, I'm going to go to exponential form. So remember what our base right here, this understood, raised to this power, should equal this number. So our understood base here on a natural logarithm is going to be e. So we get e to the 3rd power equals 2x. And now let's solve for x. We're going to divide by 2 on both sides. So that's going to give me e to the 3rd divided by 2. Now I'm going to let my calculator do that. And here we go, e to the 3rd. So let me hit second natural logarithm here. E to the 3rd. And jump it down and say divided by 2. Okay, so we got about 10.04. I think that's what it said. Yeah. Okay, now from 19 on here, what we're running into at this point is multiple logarithms. So with multiple logarithms, you only have just strategies that you can use. The main strategy here is if we have multiple logarithms on one side is to use our properties to combine them. The other thing might be to try to evaluate one of the logarithms if you possibly could, or if I have logarithms on both sides, we can cancel them off. So we'll use a combination of those three things. Now, on this one, we've got plus right here. So what I'm going to end up doing with these logarithms here is just multiplying. You get one logarithm. So now we're going to have log base 8, and we really say x plus 2 times x. So that will give me x squared plus 2x. Okay, now that it's down to a single logarithm, now I'm going to switch it to exponential form. So this base raised to that power should be equal to this number. So 8 raised to the first power, which would just be 8, equals x squared plus 2x. Now that's giving me a quadratic one. So I'm probably going to solve it by factoring. I need to set it equal to 0. And now let's look for some factors here. Factors of 8 that subtract to give me 2 would be 4 and 2. It would be x plus 4 times x minus 2 So I'll get solutions here of -4 and +2. Now I need to check my solutions. Remember, if I take a logarithm of something, that value has to be positive. So let's go back. X plus 2 there. If x is -4, then -4 plus 2 is going to give me a -2. And so that would put me taking the logarithm of something that's negative, and I can't do that. So -4 is extraneous. I'll cross that one out. Now 2 is going to be okay. 2 and 2 there will give me 4, and then that would be a nice +2. So as long as, if I'm taking the logarithm of something that is positive, then that solution is okay. Otherwise, that solution would be extraneous. All right, 21. Now this time we got logs on both sides, but we've got a little extra stuff with them. Okay, so we can't really cancel them off. And the idea, we can't cancel them off because we have a 2 right here, and we have this 6 minus on that one. So we can't cancel. Now, one thing that you could do here is you could put the logarithms on both sides and combine them, and that would work. But there's going to be an easier way here if you'll just see something with this logarithm. If you see a logarithm that doesn't have an unknown, there's a chance that you could evaluate it. And we can evaluate that. Log base 2 of 8 would be 3, because 2 to the 3rd power is 8. So really what we're looking at right there is just 6 minus 3, which would just be 3. Okay, and now we're down to just one logarithm. So we could switch it to exponential form to solve it. Now first we're going to get rid of the 2, so we can isolate it to the logarithm first. Okay, I'm just going to call that 1.5 over there. And so now we can switch it to exponential form now. So this would be 2 to the 1.5 power equals x plus 1. Now I'm going to let my calculator kind of take over from here. So I'm going to do 2 to the 1.5 power. Okay, so that's about 2.83. And now I'm just going to subtract 1 from that. So we'll get x here to be about 1.83. Okay, now number 22, again, we've got multiple logarithms. Now, notice in this one, I've got a log of 2 over here, but I can't evaluate that unless I have a calculator. So I'm going to try to not to use my calculator to do this. So let's do this instead here. Since we can't evaluate that one, let's see if we can put some logarithms together. So let's take these two and combine them here. So let me bring down this first one. And so I can actually take 2 and then 2x minus 1 and just multiply them to get it as one logarithm. So 2 times 2x minus 1 would be 4x minus 2. Okay, now let's notice all we have on both sides is just single logarithms. So we have a log on both sides and nothing else. We can just cancel those out. We'll get 3x plus 2 equals 4x minus 2. Now, let's solve it here. I'm going to subtract 3x from both sides. That's just going to give me x. I'm going to add 2 to both sides here. And so that would just give me 4. Now, let's see if 4 is going to be okay. 4 there would give me something that would be positive. If x was 4 there, that would again would be positive. Let me go back and check number 21. What's the one before that? Yeah. Again, I got 1.83, so that was okay. All right, 23. Now, this case, we've got logarithms on both sides, but it's not just a logarithm on both sides. It's 2 logarithms on both sides. So we can't cancel out here. Now, if we could use our properties to put these together somehow as a single logarithm, then we could do that. So notice you have minus right there. So what we could use there is our quotient property. So we said the natural log of x minus 5 over x plus 4. So we're actually just dividing those two values. Same thing on the right side. And so now it's just a single logarithm on both sides. So now I can just cancel them out. So what I'm left with here, this usually happens with a quotient, is you can usually just cross multiply. So I'm going to use the full method. Cross multiply here. X minus 5 times x plus 2. So that would give me x squared minus 5x plus 2x minus 5 on that side. And then on the right side here, x plus 4 times x minus 1 would be x squared minus x plus 4x minus 4. Now let's clean them up a little bit. Negative 5, x and 2x there would be negative 3x. And then negative x and 4x would give me 3x. Now, it looks like quadratics here, but notice if we bring 1x squared over to the other, they're just going to go away. And so now I just got left negative 3x minus 5 equals 3x minus 4. Now let's just solve this one. So notice this is not a quadratic anymore. I'm not setting it equal to 0. And so now let's divide by 6 here on both sides, so we would get negative 1/6. Now let's check this solution and make sure that this is going to be okay. So if I go back, if x is negative 1/6 here, that's going to be extraneous. Okay, so really you can't have the natural log or any logarithm of something that's negative. Now notice it would be okay right there, and it would also be okay right there, but it wouldn't be okay here or here. So if it causes anything to take me a logarithm of something that's negative, then it's an extraneous solution. So since that one doesn't work here, I really don't have any solutions at all there. Okay, I'm going to go back to number 20. I skipped it accidentally here. All right, so again, notice we've got multiple logarithms, so I can't evaluate either one of those. So let's put them together here. They've got the minus sign, so I can use my quotient property here and divide those two values. So this will be log base 3 of x minus 1 divided by x plus 4. And I don't have logs on both sides, so I can't cancel out, so I'm going to have to go to exponential form. So I'm going to say 3, the base 3, raised to this power, so 3 to the second power equals this value. So 3 to the second power there, 3 squared would be 9. So now we can solve this one by cross multiplying. So 9 times x plus 4, there would be 9x plus 36. And 1 times x minus 1 would be x minus 1. Now I'm going to solve this easy equation now. So that will give me negative 37. And I'm going to divide by 8. It's not going to come out too even there. So let's see, negative 37 divided by 8. Okay, so that's about negative 4.63. Okay, now let's check that. So notice if x is negative 4.63, that's going to make this value right there negative. So I can't have a logarithm of something that's negative. So that's really an extraneous solution. So it's like the last one there. We're not going to have a solution on this one. Okay, that's all.